Hey, this is Steven from Legit Tech Tutorials and the Green Engineers, and welcome back to my DIY metal milling machine tutorial series here, otherwise known as the Green Machine Mill. So halfway through my last video, or right as I was posting my last video, I realized that I should probably have a taper bearing here, so where we are going to be supporting this screw here. And reason being is that that way, if we have these two here, and then another idea is to have a plate here and have this guy actually attached to a plate or something. So pretty much what we could do is we can push these or maybe there's some sort of movement here, so this is slotted slightly here at the top, let's say, or we have two slots or whatever, and we shove this guy in. So because we have a taper bearing on the inside here and the inside here, we could smash onto the this shelf here. Let me see. This one. Let's take this one. So we could shove it up onto this support here. So smash it up onto this, and basically what that will do is that will constrain this axis here. Also, you notice that we are running a new version of Fusion. It came out 2 days ago, and so now we have all these new logos. So anyways, and a lot of different logos down here, and a lot of ways that things look different. So they're trying to universalize everything, so all their systems, Inventor, all their other systems are going to share the same, kind of logos. So that way, if you go from workflow to workflow, everything looks the same. Okay, so yeah, so basically have a tapered ball bearing over here, tapered ball bearing over here, and basically they have better support as far as if you push not radially but axially, and radial is not as good as a bearing, but it's still good, and axially it's way better. So basically what we're going to do is we're going to have this guy, and this guy's going to move in, and we're going to smash it against this taper bearing here. That way what we could do is we're going to restrict the backlash movement of this thing going back and forth. So obviously there's another source of backlash, which is any sort of tolerance inside of the screw, where the ball bearings, ball screws have way less because they actually have a ball race. So the ball bearings actually take up a little bit of that backlash compared to just regular thread. Regular thread, they have a little bit of back and forth movement that you have. And backlash happens when you turn one way and you go back and you turn the other way. So what will happen here is that because the idea with a CNC machine is that you're trying to be as rigid as possible, which means you want to restrict as much movement in places that you don't want. So one thing, we don't want this ball screw to go back and forth, right? To go back and forth in here, and that way we will restrict it. But now thinking about it, if it's so low tolerance, if it's so tight tolerance, then this guy will probably hold it. So basically, if this guy is tightly held in there, it's not going to let this thing go back and forth. But it is going to be something pretty interesting where we have one of these and then one taper bearing on the inside here. So we smash it here, and up here smash it down here, and here smash it here, and smash it here with some sort of, this one might have like a shelf or something on the inside. Maybe like, I won't machine it all the way. I'll leave like a little thing here, just like a small little ledge like that of material, and then we force this thing onto it. So that is the idea. I'm not exactly sure yet whether it is something that is super necessary, because again, if it's so low, if it's so tight tolerance to begin with, this ball screw should keep it from going back and forth. But it is a good idea to restrict everything, so we don't want it to go this way, and then the bearing for the tapered and this guy and the regular ball bearing are not going to let it go this way, left and right, or up and down. So now we have this way, which is the Y. We have the Y constrained. We have the Z. We have the X constrained. We have the Z constrained, which is straight up. And so now it can only rotate. So now we have all axes constrained, and most ideal situation. And it's going to be a couple more dollars, right? But obviously we're going to have to design it where we can push it further in. So push it further in so that we can preload. So pretty much have something here where we push on this guy on with some sort of force to preload it, and then that ball bearing in a tapered race, we'll shove it in here, and one down here, shove it in here, and this one shove it back this way, or this one shove it back this way. Probably shove it back this way, right? So that's the idea that we're looking at. So again, this guy was. So let's look at some of the geometry for these roller bearings that we need. So we're gonna replace one on each side, one here, so one on the inside, and the inside facing the ball bearing. So one over here, one here, one here, and then obviously both of these are gonna be replaced because they're both technically on the inside because there's two different ball bearings. So let's look here. This is a .591. And a .591 is a 15 millimeter, basically. A little over 15 millimeters. So let's go ahead and look at a 15 millimeter tapered ball bearing. So basically this is what it looks like. Let me put this one. Okay, so you see here, this is kind of the idea. So this is a thrust bearing. A thrust bearing would also work, but it's not going to have the axial loading. Thrust bearing is way better, obviously, in the axial. And it doesn't have very good radial support, but axial loading is really good. So basically like this. This is 15 millimeter thickness. We need 15 millimeter ID. It's too big. So we might need a oops. Okay, so it says DW, DG. Why is DG and DW two different things? Anyways, DW is that small one, and DG is the outside. So this would also work. Ball bearing, we have to do a little bit different. Basically, we have to do a counter bore. I mean, we'd probably do a counter bore to begin with on this other one. So that's another thing. I don't know why I drilled all the way through. In the ideal case, we do a counter bore on this other one. So we have a shelf where this bearing doesn't go all the way in. So basically, we have a counter bore that goes this depth and this depth. But this is a little different because you need both of these to rotate. While taper bearing is a little different because you have I have a lot of projects that use thrust ball bearings. They're really good for low tolerance stuff because this could have some slop back and forth, and it's really just to get rid of load on the motor bearing. So if you have a motor with a direct drive shaft and you're pressing on something, for example this screw, you want some sort of bearing to take the load off of the motor. So if if I already had, this would be something good, but as you can see, this piece here stays stationary, and this rotates, as well as the ball bearing race here rotates. So you have to have a counter bore, but the counter bore can't touch the side of the DW. So basically, you need, this has a little bit of clearance here, I believe, so you basically have to have this piece popping out, and every time you take it out and put it back in, it could fall off. I mean, same deal with the taper bar bearing. There's nothing that holds it in there, so it could just also fall right out. This one's 15 and a quarter millimeter. So what is that? That's about 10 thousandths. That's so about 5 thousandths a side. That's a little too big. There we go. SK. So this one looks like, it says it's tapered. $11,000 RPM. We're never going up to that, so don't have to worry about that. Interesting, but $25. So you're talking 1, 2, 3, 4, 5, 6. You need 6 of them. So that's almost $150 worth. 15 millimeter bore tapered. This is a roller bearing. Most of them are roller bearings. Okay. But this one doesn't have a race. What's the point of a roller bearing window? Okay, now there's more popping up. It's a 15 millimeter bore, 25 millimeter bore. Here's an exact 15 millimeter bore, $12. That's better. Here's an Amazon, only one in stock. $13. Here's $6. Yep, so this is exactly what we're looking at. So basically what happens is you make a counter bore that is 42 millimeters in diameter and 13 millimeters thick, and then you shove this, you put this guy, you press this guy into the counter bore, right? And the counter bore is obviously got to be very flat at the bottom, right? It's got to be extremely flat at the bottom and pretty tight so that you have everything centered. And then this piece is all together. You see the race here with tapered, and then this here has the rollers with the basically the bearing race. And what that does is that you see here that if you press a load, it basically pushes this against this. So it's very, very good. It's obviously not as good as the what is it? The thrust bearing, because that's the idea. Is the thrust bearing? That's why it's called thrust bearing. Is that it's basically ideal to support just forcing loads. But if we wanted to have only one bearing, this would be one that you would do, because it's basically 45 degrees of a regular bearing, so it has support this way, right? And it has support this way. And when I'm saying this way, obviously I'm talking about you have to have something bottom out right here, which it looks like it does. So it does have something to bottom out. And I am using this on one of my projects for the Fill Factory, which we will go over at a later time. So let's see if we could get something like this to work at $6.60, probably from China. Looks like it's from China. Well, that's okay. So, and that's, you know, I think the other ones we were looking at were like $4. So the regular bearings. So let's go ahead and design one. Well, let's see first if they will fit. So these are 42 mil. That's the issue, is that they're very, very big OD. So it's a 42 mil OD. 2.0 2.283. Oops. So let's look here. 2.283 is 57 millimeters, and we need 42. So that's basically 58 millimeters. 58 millimeters, so we have 16 millimeters left. 16. So we got 0.63 left. My calipers, so that's 0.3 on each side. That's plenty of meat. Okay, so we can run that. I think this one's pretty close, I think. This one is, this one's only 1.378. So it's only, this is a 35, right? So this one's a 35, and these ones are 42. So 7 mil over. That's only a 1/4 inch. It's only a 1/4 inch over, and so each side that's about 1/8 of an inch. So it's not that much bigger. Okay, so let's go ahead and design one here. Let's drop in a design here very quickly. So let's do a circle here. So we have a 15 millimeter bore, and we have a well, basically, I'll show you guys in a second. 42 millimeters actual outside, and 31 millimeters total. Oh, sorry, 13 millimeters total. Okay, so that's basically what it looks like. And so let's save this. Let's call this U Excel 3032 tapered roller bearing. Cone and cup set. So the cone is the bearing part, and the cup is the part that the cone goes into, right? So you have male and female. The female part's the part that doesn't move. Okay, so another thing to bring up is you can see here that 13 millimeters is actually from the end here, not exactly how deep that counter bore has to be, because we don't want it that deep. I mean, it can be that deep because you can see there is clearance, right? So there is clearance. This doesn't get anywhere close, right, to this side. So it's not going to rub, even if we do indeed do 13 millimeters deep, right? And then obviously if we do the 15 millimeters here, just like it is on this shaft here, and let's say that we get rid of this. Oh, not that shaft. This one back here. And then you can see here that what happens is when we get to this one, it is 0.787. 0.787. Oops. So that's about 20 millimeters. So, ooh, that's not a lot. I don't know if these are really designed for this kind of deal. Because what that is, it's only 2.5 millimeters this way, 2.5 millimeters on this side. That's not a lot of room. And if that's where the thread starts, then there's not going to be, because the thread obviously is not solid, so it's not like we actually see here. Because basically this piece here is not, it's not solid, right? This is where the thread starts. So if we look here on my calipers, so what is it with? Mm-hmm. 15, and this one is 20. So that's, yeah, 2.5 millimeters. Which is very small. 2.5 millimeters is about, about 1/10 of an inch. Right? 2.5 millimeters is about 1/10 of an inch. Yep. Okay, so it may work. But then again, for the low forces, well, then again, there is going to be forces, which is pretty much everything that is pressing against the this piece is going to be pressing against your bearing, right? But it's pressing it all. It's focusing all that energy over a 0.10 millimeter area. I mean, 0.1 inch area, right, on each side. So, I mean, technically, it has a decent amount of area of the bearing stress that it's. I mean, you can see it here. This is all that it's going to be touching, and that piece is going to slide right on top of this guy, right? But if you think about it, as far as force-wise, when we move this piece, if we're going to move into the cutting forces that are going to be required are going to be pushing, because you have reaction forces, right? This guy is pushing this way, and that means that these guys are basically going to be transferring the force. So what we have to look is where are those forces parallel to some of our motion stuff. So you see that if that ball screw wasn't there, this thing would just move, right? Because these are in the same air in the same direction as the force. So let's say that we're pushing this table into the spindle. Spindle's here. We're cutting material. So we're forcing this in. If that ball screw wasn't there, it would just move this because these rails are not going to hold it. These rails are just going to let it slide right back. So the things that are going to hold it are these two, which are in turn attached to these. So we're going to look at where they're attached. So all these four blocks are attached to these four. So number one, these have to resist all of that force, pretty much. These four blocks, right? And then these four blocks transfer to these other blocks, which again will move besides just this screw. So where a lot of your precision comes in is how much you can hold on that screw, right? So if that screw moves at all in here, you're going to see that tolerance in this cutting. So we need either a thrust bearing or a radial bearing. So I agree with changing this here. So let's go ahead and change this. So let's open up this. And we have the counter bore now. So we'll just do the 13 millimeter depth. And that'll also strengthen this guy a little bit. And we're going to pick a side here. So let's see, sketch. And so obviously we're going to need two different sketches. So what we'll do is we'll leave that one through. I mean, it really doesn't need to be through. And this is basically just 15 millimeters. Alright. And so let's just pick this side as our side for the big boy. So this is going to be 42 millimeter OD. Oh, it's thin here and here. It's not that big of an issue, but I might be able to find something smaller. But in the meantime, we'll get the idea here for negative 13 millimeter. There we go. And then there's a hole there, and now we have this guy, and then so now let's look at this guy, this bearing. And there, this is our regular bearing that we're going to be using. And then this is 0.433. So let's do it here. 0.433, and what is this? 1.378. 1.378. Yeah, so you got a lot more meat here. And then again, this is 0.433, 0.433 back. Minus 0.433. There we go. And that is our new block. So this side for the taper, this side for the regular bearing. And whether or not we actually, at this point, need a regular bearing, that's really up to, what we think about it here. I think it's a little overkill, but it would be nice to constrain it so we help support this end here as we're rotating it. Or we could have this guy go all the way through, and then we have the bearing here. Okay, so let's go here and see what gets messed up. And we're going to have to flip and flop stuff around. Oh, and then another thing, we're going to have to go ball bearing support assembly. And then we're going to get rid of one side. This one, get rid of that one. Delete. They have some UXL stuff. They're pretty good as far as Chinese stuff goes, I think, personally. Where'd the other one go? Oh. There we go. Okay, so now we have the bigger bearing on the outside, smaller bearing on the inside. Now hopefully this doesn't rattle that much. Ooh. I mean, it is steel. I mean, there is that. We'll have to find something with a smaller OD, because really the OD is not gonna do much of anything against us here. So let's take this one. Where's our first one? Okay, that's this one here. We need to show this one. Where is it? This one? This one? This one. And we're just gonna flip it 180 degrees. And then we're gonna press it in there close to what it's supposed to be. Let's see here. What was his depth here? 0.1662, 0.1662. Oh man. I mean, you get the idea here. What? Oh, there's a dot right there. Delete that. There we go. Perfect. Alright, small bearing on the outside. Good. Okay. This one's next. It's on the wrong side. That's okay. There we go. And we should have one more, two more. Oh, I forgot to do that other one. So we could do that other one. So this guy is gonna be here. Wait a second. Yes. And then in 1.662. Okay. And then that guy. We got this guy. Okay, so this guy now, did I put, so let me open up this and the assembly, and let's close this, close that, close that, close that. So in the assembly, do I have 2 bearings? 1, 2, 3, 4, okay. So that's good. So there's obviously no way of doing this counter bore on the inside for that one. You can do a counter bore for these two. And you can do a counter bore for the top. So let's see. This one first. Okay, that's good. That one's fine. This one, we're going to just do 15 millimeters. And we're going to do 2 counter bores. And I should not have closed this one so I could see what those counter bores are easily. Oops. Oops. Now let's go ahead and, oh, not that one. That one. And let's go ahead and do this one. This is a 42 millimeter bore. 42 millimeter. Okay. And then we're going to roll back to this point here. Yeah, this point. Actually, no, this point. And we're going to extrude sketch. Not first sketch, second sketch. And then this goes in 13 millimeters. Okay, so there's the first counter bore. Obviously that other hole will have to be bigger, but that's going to actually come with how big the piece actually is in real life. And then we're going to need to do this back side here. And this one is some sort of 1.378, 1.378. 1.378. Okay. And again, let's look here. 0.433. Okay. And we'll obviously have to do some clearance here, but we're going to do everything as assembled, and then we'll measure it to figure out, we'll buy some of these components, measure them to figure out the tolerance, and then go from there. So this one, what we're going to do is we're going to do 2 holes. This one, ooh, is 45 millimeters going to fit? 42 millimeters? 42 millimeters? Yeah, it's going to fit. So what we're going to do is we're going to do this one, these 2 down, and that's going to be minus 13 millimeters. Then we're going to pop back up this sketch, and we're going to punch this all the way down. Uh-oh. So interesting. We're going to lose some support here. But we don't need to go all the way down, so let's see here. Ooh, do I have the 15? The 15 needs to be obviously punched all the way down. But this doesn't need to be punched all the way down to remove any sort of something like that. So let's go here. Okay. And so basically what we're going to do is, we're going to do another punch, and because we want some different distances, and you see there, no problem. Bam. Looks good. Do we have some section analysis? Does not look like we do. So let's go ahead and inspect. Oh, and they added some more stuff here. There's some different machining stuff. Section analysis. Boom. Okay, so first bearing goes in here. Last bearing is pressed down here. And then here, so obviously in the bearing, we're going to look, the bearing that we buy, we're going to make sure, we're going to see what this inner race is, because the inner race is going to spin. So obviously this hole is going to be a clearance for that inner race. And you see here that they line up. And so you press in the first bearing, you press in the taper bearing, and you're good to rock and roll. But obviously if those bearings fail, this is basically garbage, right? So anyways, let's go ahead and save that. Oh, we're at 36 minutes. Holy, yeah, we're at 12:45 right now. And obviously, like I said earlier, tomorrow we are going on vacay to. So that's okay. That one's not, and that one's not. So tomorrow we're going on vacay to Palm Springs, and then I'll have to catch up on videos at that point. Sure. Flip it. Good. Fine. Just gonna ask. Oh, I didn't ask capture position that time. Perfect. Okay, so now what about this one, this one, this one, and this one? Wait. Oh. So that looks to be about, oh, okay, so I do have some analysis here. Oh, wait. Is it in the right spot? And then unflip it. Bam, bam, bam. And you see we have clearance here, we have clearance there. Okay, everything looks good. Alright, so that is basically it. Let's go in here. And hopefully I picked the right spot, otherwise we have to rotate it. Let's see, did we? What? Oh, we forgot to save it again. Save it again. Custom layout update. And it looks like we did pick the right spot. Okay, looks good. Alright, so this has been Steven from Legit Tech Tutorials and the Green Engineers. I thank you guys so much for watching, and I will catch up sometime next week on all the videos that I'm missing. I'm gonna figure that out. But I'm gonna be back Sunday night, so I will be able to film my programming videos if you also watch those. Alright, so I will catch you guys in the next one. Take it easy. Peace.